Started. Welcome back. I'm sure you had a exciting rude awakening this morning when the alarm went off early and said, okay, I got to get to class. Let's get started where we left off. It seems like a while ago since I've seen you. I guess it has been a while ago, and in your case it's almost 2 weeks since the last time I saw you was on the Wednesday of the last week. But as you're coming in, grab your test. I'm going to assume that you guys got my email that had number one, it had the solutions on it. Number two, it had the link to the different videos and the examples I had done. And 4 of those 5 on the test were almost identical copies of what I did in class, so I hope the link was somewhat helpful. Also, as you came in, and I see a lot of you are picking it up now, so good, continue to pick it up. I hope that now that you have them, you can go back and look at them. And so I thought, since we're in that very busy time of the semester and very detailed time, and it's been so long since we actually took the test, that I'm going to let you grab it. I'm going to let you look at it. It was not an easy test, as you know, so chances are for most of you there's some errors and significant errors that you're going to want to look at and understand why it wasn't right. But I thought between you getting them back today, plus the fact that I sent that link, if you didn't get that link, take the time today to then take your test, go to your Pipeline account, and look at the PDF solutions that I passed back to you, as well as the video links. And so, as I said, 4 of the 5 we did in class, and so I gave the timestamp. So go to the link, go to the timestamp, look it up, and you'll see me work out a nearly identical example. That first one probably hit people the hardest. It was kind of a different problem. We did one in class like an ice skater like it, so I'm going to encourage you to go and look at that one. All that being said is a long way of me saying here, you've got the test, you got the solutions. I know you're still going to have questions about it, so please ask, but it's for in class today. Let's move on into chapter 10. We've got probably the hardest chapter of the semester in front of us right now. You just had a long one, chapter 9. I hope you took the time over spring break to make sure you did chapter 9, as I was mentioning before spring break. And now as we get to the other side here of spring break, and we get in this chapter 10 and 11, but particularly 10. 11's a hard chapter too, but it's at least short and hard. Whereas 10 is both hard and long. And so I really want to dive deeply into that. I encouraged you before the break to, if you had time, to make the time to look at chapter 10. Some of you, I know you did by the emails you sent me. If you didn't, that's okay still. But remember, we're back. And hopefully you're back and well rested, because it will probably be 4 weeks before you get any sleep again. And so as we do these next 4 weeks, or is it 5 weeks? I'm not sure what it is. Something in that category. I should probably count them out. But we've got some tough material as we get a little bit more into it. Fortunately, the other side of chapter 11 is a little easier, but that's kind of what is in front of us. So let me say it again. You have the solutions. In fact, I brought my copy here that I scanned and sent to you, because I thought people would have some questions for me, say after class or in the lab. And so we're going to go in the lab today. We're going to do a conservation of momentum. It's a straightforward lab. Plenty of time to ask me questions afterwards. Although I am going to make this note for those of you who are in the later labs, the 2:15 or the 5:30. We're going to have a sub today. My son, actually, who's in high school, they just started their spring break this week, and he's going on a mission trip, and so I need to get him to the airport and all those good things. So I've got a sub coming in, and timing just worked out actually really well, because it is a straightforward lab. Those of you who had 102 within the last couple of semesters will both recognize the lab, because we did this lab in 102, almost identical, and you'll recognize the sub, who's Dr. Kelly, who many of you I know had for 102. So he's going to come at 2:15 and then again at 2:30. So that will be good, I think, all the way around. In fact, when I see him later today, I'm going to leave this solution with him in case you guys want to pick his brain and look at the solution with him. That's fine too. That being said, let me come back to one thing that I did say after the first test, and I'll repeat again here, is that looking at your breakdown, now that you've done the first test, which is the easier kinematics, and now we finally get into our dynamics here, take the average of those two. See how you're doing overall, because as I was saying in the first test, and let me repeat it now, if you can keep your test averages at 86% or higher, and then, of course, do the homeworks and the lab, and then your overall class average will be greater than 90%, and that will give you an A. I do some curving, although I do that at the very end, so I'm just going to say your best bet is to shoot for 90%. Then you know for sure you're getting an A. If you get that 89%, I can pretty much guarantee you'll get the A minus at that point. But how much curving below that, I kind of wait until the end to see what the average on the test scores are, and that way I can kind of gauges me on, on how difficult did I make the test this year versus last year versus the year before, and so forth and so on. So I look at past years' averages and kind of decide on how much curving I get. Same thing can be said about the second level. Again, if you keep your two test scores above 73%, and of course if you do all the homework in the labs, that'll get your whole class average at 80%, and again that'll guarantee you a B in the class. And again, probably if you're at that 79 or 78%, you're going to get the B minus here. Then, and the same thing with the C grade. And since the C grade is as low as 60%, and just the way the numbers spread out, then if you got your test average above 47%, together with all your homeworks in the labs, gives you in class above 60%, which is that C grade. And so there's kind of those three breakdown ones that I have. So, like I said, with that in mind, let's jump into Chapter 10 here and see what Chapter 10 has to offer. If you had a chance to look at it, great. Maybe I should point out the homework packet. I know we just took that test on the Monday before we left, so there was a number of you over the break who said, oh, I forgot to pick one up, and so if that's the case, pick one up now. I will say you're behind, so make sure you do double time this week to get Chapter 9 done, because Chapter 10 is going to be due Monday, and that means this weekend you have both 9 and 10 to do, the two longest chapters, and arguably maybe the harder of the chapters of the semester. So what is Chapter 10? Well, I alluded to it on Wednesday before we left here. You might remember us trying to find the center of mass. I decided to bring a hammer out here today and say, okay, where is the center of mass of the hammer? Well, we happen to mark it here with some red tape here. But as we were working out in Chapter 9, there was an important reason we cared about the center of mass. And as a quick review then, and I won't actually throw it across the room. Actually, I did that one time and I chipped the handle here. But if I were to toss this across the room, wouldn't there be an outside influence of gravity? And the inside influence would be the forces between all the molecules. But as we said here at the end of Chapter 9, the intermolecular forces, the internal forces, do not control the motion. Those forces all add up to zero because of Newton's third law. But the external force, which in this case is coming from gravity, controls the motion of the center of mass. And so everything we've done up until this Chapter 9 had been thinking of our objects as little tiny points. But the reality is they are not little tiny points. And so for the first time this semester, we said, let's give our object size. And so when we did this in the second half of chapter 9 here, we said there would be one magical point, called its center of mass, that would follow that parabola that we've been discussing since chapter 4. The other points then on the object do not follow a parabola. They would then be spinning around that. And so this object, as it moves through the air, is going to have the magical point, the center of mass, make a parabola, and the other points on the object are going to make circles around that parabola. So, here's our strategy. If we can look at both the projectile motion, the parabola, and the rotation of it, can't we put the two together to get the total motion of, say, this point right here on the end of the hammer? And that's going to be our goal. And we'll put all that together in chapter 11. Chapter 10 is not quite as complex as I just described. Chapter 10 is, say, let's take an object such as this, and let's just talk about rotation. Let's not have the axis of rotation move yet. Let's just talk about it rotating around what we'll call a fixed axis. So that's where we get started in chapter 10. By the end of chapter 10, we'll let the axis move a little bit. We'll do something more like this. We'll say, let it rotate, and then we'll set it on the table here. And so the axis will then just kind of move a little bit, but it'll be a straight line. Chapter 11 is when we finally get to the grand finale. We'll throw the hammer across the room, and then we will say there's the outside influence, which makes a parabola, and then we will have circles around the parabola. So that's kind of my introduction here to this long chapter 10, as well as leading into chapter 11. And this is then the title. What is the rotation of a, and this is going to come important here, rigid object, or we'll use the older phrase, rigid body, about a fixed axis. And so I'll say it again. Here is what that phrase is. Here's an object that is rotating. This is the axis that it's rotating. In this case, I would say the axis points along the z-axis. So I have a z-axis of rotation. It's not moving, so it is a fixed axis of rotation. The object itself, this wheel, as I spin it, it doesn't change its shape. You could imagine that if these spokes were not strong pieces of metal, but maybe were bungee cords, if I were to spin this, you might imagine, maybe more like spinning a water balloon or something, you could imagine the object deforming, right, and stretching out, and elongating, if you will. And that is not going to happen to us. That's what we mean here by a rigid object. So when you dive into these problems, you will quickly see we are doing the simplest and easiest cases we can of a rotating object. It makes sense. It's a place to start. Although I must say, when you do get involved in them this weekend, you may not feel like these are the easy ones, but these are as simple as we can make it, right? This is where we're going to have rotation, but as simple as we can. Fixed axis, not moving, rigid body, so the object doesn't change. So let's have a discussion. And in fact, on the sideboard over here, I am going to put a little chart, because I think the best way to understand translational motion here is to, or excuse me, the best way to understand rotational motion is to look at the translational stuff. And we will see then by the time we're done with this chapter, and chapter 11, I guess I should say, that everything we've done for translational motion, we are about to repeat. So, the good and bad about this chapter is, the good part is, you've seen everything. What could make the chapter easier than that? We've already done it. Now, we've done it for translation, so if you can see the analogy, it's that simple. We've done a lot of stuff in the last 9 chapters. So maybe the bad news here is we are about to do 9 chapters in 1. That's why this is a long chapter, right? Everything we've been doing from the beginning, we are going to repeat in 1 week, in 1 chapter. Makes a nice review, but it also is a lot of material. And so you'll see here, and I'll begin to fill this in. And so for the next 2 hours, we will fill this in. What did we do in chapter 2? What did we do in chapter 3? What did we do in chapter 4? What did we do in chapter 5? And we'll talk about all of those things. Maybe not in numerical order, because it's, as you'll see, it's sometimes better that we don't do them in the exact same order that we did for translation. But you will hopefully see the analogy. And like I said, it's really good in that sense, that it is a good review. And if you understand what we've done up to this point, then you'll see how easy this chapter is. And hopefully the homework will be easy for you. If you miss the analogy, then you will see how much material there really is in this chapter. And it'll feel like you are doubly lost because you didn't get it for translation, and you're equally as lost when it comes to rotation. So I hope that's not the case for anybody, but it can lead to that. So here's what I'm going to do. I'm going to go ahead and just put a grid on here and say, let's just take an object. Who cares what kind of shape it is? I'll just imagine, if you will, here's a piece of plywood. So a piece of plywood, I go out to my garage, I take a jigsaw, just give any shape you want to it. I put the object up against the wall, I take a hammer and a nail, and I drive a nail right through it. Now, this is not necessarily the center of mass either, by the way. Just some point, just some random point. Could be the center of mass, could not be the center of mass, okay? And then, let's talk about it spinning. So there would be some point on here. And then, so maybe if I took a little spray can and said, okay, I'm gonna spray paint this point. I'll call it point P. But what would happen if I took that piece of plywood, now with the nail through it, and I just spun it? What would happen to the point P? Now remember, I got a fixed axis, I got a rigid body. What does that tell me? Right, and so the reason that the rigid body is going to come into play here is it does not matter that the piece of plywood itself is not a nice circle. What will happen to point P though? Point P will make a nice circle. And so this distance R is the radius that the point P would make going in a circle. And in fact, pick another point. Instead of point P, maybe I'll pick the point Q. What do you think would happen with point Q? Yeah, exactly the same thing, except of course now we're talking about a different radius. I get that. But the point is that the axis is fixed, the object is rigid, its radius is then fixed. Doesn't matter how fast you spin it. This is not a flexible object here, okay? And it will always keep that same radius. And so point number 1 here is, hopefully you'll see here that all the points on this object, doesn't matter what shape it is. It could be rectangular in shape, or it could be this crazy shape that I'm talking about, or it could be circular in shape. But all the points will then make a circle as they go around. Now we're going to take advantage of that. And you can see then making them be a rigid object is obviously the part that makes it much easier than if the object changed its shape while it was spinning. So good news here is we won't do any of that. We will get you ready for your next mechanics class where you will work with semi-rigid objects, and they do change their shape. But for us, this semester, in fact, these 3 semesters, which only this first semester is any mechanics, we'll just have rigid objects. All right, let me keep labeling up here. Let's go back to the point P. I might label the angle of that radius from the x-axis as the angle theta. And again, this is exactly like the notation we used in chapter 3, isn't it? Where we did polar coordinates. We said, look, where would you describe, or how would you describe the point P on that object? Well, polar coordinates is one way to describe that. Let me add something we didn't do in chapter 3. This length here. I'm sure, though, in your math classes, you called that the arc length, right? How far is the arc? I suspect you probably use the symbol S in your math class. It's kind of the classic symbol for arc length. Does that look somewhat familiar? All right. But let's talk about the motion of this. So as this thing spins around, R doesn't change. Doesn't theta change? And then S is really kind of that distance it's traveling. And theta is that angle. I bet there's a mathematical connection between these 3, isn't there? Do you remember them from your math class? How is arc length? Yeah, theta times R. All right, that is the arc length. Although, it's the way the Greeks defined the arc length. What do I mean by that? Theta is measured in what units? Radians. So this works in radians. In fact, the Greeks defined the angle kind of the reverse of this. They said take the arc length, divide it by the radius. That is your definition of an angle. But let me emphasize again, in what units? Radians. Because I think up until this point we've mostly used degrees. And so we're going to use a lot more radians. So you got to know what mode is my calculator in as I go to work on these problems. So notice that if you're going to use this equation, or maybe I should even say this equation, you must be doing the angle in radians, not degrees. And so there is maybe point number 1 here. In fact, maybe I should even put that on here, the units. The units are in radians. In fact, let's talk a little more closely about the unit radian. Let's look at this side of the equation. This is the arc length. What units would you use here for arc length S? Yeah, meters. How about this, the radius? Wouldn't that be meters also? And so a radian is really a meter divided by a meter, which is what? It's no units, really. So if you haven't caught this from your math class, notice that we often say radians are real numbers, meaning there's no units with them. We only put them for clarification. If somebody asks you, what is the angle? You could say, oh, the angle's 90 degrees. Well, okay, 90 degrees, right angle. Clearly, you are measuring it in degrees. But another way of describing a right angle is to say the angle is pi over 2. Well, pi over 2 what? Just not needed. It's just what? Pi over 2. Now, I admit, we often say pi over 2 radians. Just to make it real clear, we're talking about real numbers and not degrees. But the point is, there's not really a unit here. So radians we can throw in for clarification, or we can take it away for clarification. Whichever is the best way to describe it with or without radians is not a real unit. That is an important observation here. Because I'll tell you, I get this question, you probably asked it yourself, and you probably will again this semester. You're working on a problem and you go, I wonder if my calculator is supposed to be in radians modes or degree modes. We'll look at the units. Is it real numbers or not? If it's in real numbers, well, the answer is radians. It's that simple. If it's in some other units like degrees, then it should be in degree mode. Gradients aren't really used much these days. I don't even think you guys have gradient modes on these modern calculators. But grading was a great idea that used to be on the calculators and kind of died away. But it's take a right angle and chop it into 100 pieces. So then you have a decade system instead of a 90-degree system or an irrational system like pi over 2. So I probably shouldn't even bring that up, but here's my point. My point is radians is a clarification. It is not a unit. So if we don't see any units, then for an angle, then we know it's in real numbers. We know that is radians. And we know our calculator is supposed to be in radians. And that's what you'll begin to see. But I hopefully answered this first part here. When we got started way back when we first did our physics, and I'll call it chapter 2 since chapter 1 really wasn't about physics. It was more about units and unit conversion. But I'll throw that in there too. We started off and we said, how would you define the position? And what we had is things like x is its position. It's measured in units of meters. And so what I'm trying to say here is we now have its angle. What is its position? It's not a translational position, it's a rotational position. And so as this object goes in a circle, what angle is it at? And so its angle changes. What units would we use? Well, I'll put down here rad for radians, but again, we may just have no units because no units would imply then radians. And that's what we did in chapter 2. Subtly in chapter 2 came from chapter 1. We would have things like 100 centimeters is 1 meter. And so some of our problems in chapter 2 gave things in centimeters or kilometers or sometimes even feet and inches. And we would have to convert them from, say, inches into centimeters into meters. Well, same thing here. 180 degrees is pi radians. And so again, don't be surprised then if we have to do some unit conversion. And so there's the beginning of what I was trying to say is a repeat of everything we've done. Going all the way back here into chapter 1 where we converted our units, and chapter 2 where we started off by saying, describe the position of it, give me the units for it. That's what I'm trying to say here at the beginning of this chapter. I'm going to have something that's going in a circle. I need the units. I need to be able to convert the units, and I need to describe what is the position of point P or the position of point Q as it rotates around. I'll continue on. I'll put a line under this and say, okay, what did we do after we talked about the position of the object? And if you recall, we said, how quickly does its position change? At what rate is it changing its position? We called it dx dt, right? The instantaneous speed. How quickly does the object change its position? What do you think the next step here is? So I have 3 objects. A green one, a yellow one, a red one. I spin it. At one point in time, I can talk about its position, but couldn't I also talk about the rate at which its positions change? What do you think I should call that? Yeah, it's speed. More accurately, it's rotational speed, or sometimes an angular speed. So again, since we got so much time, so much to cover in such a short period of time, let me not take too much time to just remind you then that we had this thing called an instantaneous speed or velocity. To be more particular now, we will have an instantaneous angular velocity. How quickly is it changing its position? But of course, I'm talking about its rotational position. And so we'll have an angular velocity, or what you called a rotational velocity. Any guesses on the definition? Yeah, it would be the limits as, say, time goes to 0 at the rate at which its position changes with time. And so again, hopefully this comes all the way back to chapter 2, where when we did translational motion, we took the limit as time went to 0 as the position changed with time. Of course, then we invoked our calculus and said, all right, that limit, that short amount of period of time, would then be a derivative. And so the connection between position and velocity was the derivative. Hopefully not a surprise then that the connection between the position, angle, so angular position, and its angular velocity would also be a derivative. What might be a little bit new here is the symbol I am going to use is the Greek letter omega. It's not a W. It's kind of little wings on the side there to say it's a Greek letter omega. And in fact, maybe now you're beginning to see a pattern. What do you notice about rotations? Yeah, to keep things straight, we'll do the symbols in the Greek alphabet. And so translational ones, we're using the Latin alphabet, and then for the rotations, we're using the Greek alphabet. There is an exception coming up here, but other than the one exception, which you'll see why the exception's there and the value of that. Oh, actually, I guess two exceptions. There's another one in the next chapter, but one exception this chapter is that we will use the Greek alphabet. And you've probably been doing that. I don't know if you've noticed it, but I bet many times in your math class you've been doing like the triangle. And you've been putting angle theta. And if you needed to label another one, you would do things like beta. And you would have alpha and beta and gamma and delta and all kinds of other Greek letters. Phi is another one that is used a lot, right? And so, because we're talking about angular stuff, and so we have a tendency in the science and math fields to use the Greek characters for that. Anyways, so doesn't surprise me that this is an omega, which, by the way, is usually a clue to how well a student understands if they come up and start asking. I solved for W, and I got, W. If you think that's a W, you just missed kind of the bigger idea that all of our rotations are labeled in the Greek alphabet. Okay, so there's our omega. What would the units be? 1/2. Okay, good. You can see here there would be this unit of radian, or no unit, and a second. So we can say it's so many radians per second, or just per second. Although I must say, calling it radians per second, I think makes it a little clearer. If you were to say something had a rotational or angular velocity of 2 pi radians per second, that means it would make an angle of 2 pi every second. Now 2 pi is a full circle, so we're talking about a full revolution every second. And I guess in 1 minute then that would be 60 revolutions in 1 minute. So you might even call it 60 RPMs, which is another unit used for rotational speed. So we might have to do some unit conversions from RPMs to radians per second. Noting that obviously there are 60 seconds in a minute and there are 2 pi radians in 1 revolution. And so this whole idea of converting units is going to come into play. So again, more of repeating chapter 1 and chapter 2. Well, I'll continue on. Because again, what did we do next in chapter 2? After we talked about the rate at which it can change its position, we said, we talked about its acceleration, right? We said, at what rate could an object change its speed? And so we would have an acceleration. Now, to be a little more accurate, for today anyways, I will say I want to talk about its angular acceleration. And again, moving along fairly quickly, since we've got 9 chapters to cover here this week, what do you think the definition for angular acceleration is going to be? Yeah, the limits of how the angular speed changes with time. Using our calculus, then, that would be d omega dt, right? At what rate does its angular speed change? And maybe now you're catching on. What symbol should I use? Maybe now you remember why they listed the Greek alphabet there in chapter 1, right? So it won't hurt to go back to chapter 1. But in place of A, we will put the first letter of the Greek alphabet, alpha. And so here we will say meters per second squared were the units for measuring the translational acceleration. So there was our definition of translational acceleration way back in chapter 2. We're going to add to that now and talk about a spinning object or rotating object here. And so we will have d omega dt is alpha. And so we'll have an angular acceleration. At what rate does it change its angular speed here? And so things that rotate, a hard drive on your computer might be a real good example, because I suspect your computer, like mine, is probably going to sleep right now. And when you return back to it, if you listen carefully, you'll hear the hard drive go, ooh, and it goes faster and faster and faster, and eventually gets up to, in my case, I have a 7,200 RPMs, and that's revolutions per minute, so I can convert it to radians per second if I wanted to, but that tells me then the acceleration. It takes about a second for mine to build up to speed. So I can tell you what the change in speed is, how much time does it take. That would be the angular acceleration of my hard drive there. Units, of course, then would be radians per second each second. Or without the radians, it's just per second squared. But again, I think putting the word radian would be really kind of useful here in terms of defining then the, or making it more clear, I guess I should say. And so I trust you remember all of these. In fact, I'm going to put the same little symbol here on the board that we did back in chapter 2. We said, all right, now, if you have a problem that you're going to solve, let's just say, I mentioned the computer hard drive. How about a different example? How about a propeller on a prop plane? And so maybe this propeller, maybe you just landed and the pilot turns off the engine. And so it's going to be spinning. It's going to be slowing down. It's probably going to be slowing down because of air resistance. Oh, sounds like a fun problem, huh? You know, a little air resistance, a little slowing down, a little de-acceleration there. How many times does it spin before it comes to a stop? Or maybe after 3 seconds, what is its angular speed? But if I put here position, angular speed, angular acceleration, I'm hoping that this little chart looks exactly like we did in chapter 2, right? If you know one, you can get to the other. And likewise, if you knew acceleration, you could get to speed. And if you knew the speed, you could get to position. And so that was the little chart we saw in chapter 2. And so again, hopefully by analogy, all this looks pretty straightforward. It's like, oh yeah, you know, I've done all these. And in fact, what if we did this? What if alpha is equal to a constant? So let's go back to that prop engine, but now let's say it's not slowing down because of air friction. Let's say it's slowing down because there is a braking mechanism in it. And so the propeller is spinning around and there's a little brake. And we learned here, right, that the friction would be a constant value. So it would have a constant acceleration as it's slowing down. Could you tell me the equation for the speed? Well, I bet you could. And I'm hoping it looks just like we did in chapter 2. Doesn't the speed come from integrating the angular acceleration? Isn't that this step? And you might remember we did this in chapter 2. It looked more like this, though. It had velocity equals the integration of acceleration times time. But what was the first thing we did? Well, we said in this special case, with the acceleration's a constant, we can pull it out of the integral. Then when we do the integral, we would get alpha t, and then we would get some constant of integration. And then we would step back and look at that constant of integration. And we said, well, this is the speed, but when time equals to 0, the speed is c1. So let's give it a name. Let's call it the initial speed. And so what we would have is we would have this first equation. And it's exactly the first equation, except it has to do with rotation, that we saw in chapter 2. We have the angular speed is equal to the initial angular speed times the angular acceleration multiplied by time. And hopefully that looks like exactly the same thing we got when we did for translational. So again, both the easy and the hard of this chapter. The easy part is everything we're going to do in this chapter we've already done. The hard part is then, of course, now that's a lot of material. Okay, but that's our first kinematic equation. So just like in the problems we did in chapter 2, we would ask ourselves, if we're reading a problem and it says, how far did it travel? Or how fast did it travel? Or what is the acceleration? And I should say, what is the constant acceleration? Then we can use that equation, right? That equation is valid. It's valid only for constant acceleration. As you probably recall from chapter 2, we would not try to use this equation if we had a non-constant acceleration. In fact, on that first test, there was one problem that had a non-constant acceleration. And I put it there purposely to see what you would do. Would you continue to use these equations of constant acceleration? And most of you saw it right away, and you did not use it. A few of you did use these equations, and hopefully you learned that lesson. You would never use it again for things that didn't have a constant acceleration. So I would say the same thing here. As we begin to do the problems, and as you begin this weekend and you open it up and it talks about, say, something speeding up or slowing down like a hard drive or a car engine or something that has rotation with it, you're going to ask yourself, then is this a constant acceleration problem? And if it is, you'll use this equation. In fact, let me take it one step further. How would I get the equation for position? Well, again, what did we do back in chapter 2? It was this step here, right? We integrated. We took the equation for velocity, we integrated it to get position. So I will do that here. I will take the equation for velocity, which is initial velocity plus acceleration times time, and I will integrate it. Now what do I get? Well, I get initial velocity times time plus 1/2 alpha t squared plus some constant of integration. Now let me call it constant number 2 there. But if I study constant number 2, you'll see that what constant number 2 is really saying in here is the value I get for its position when that and that is time equals to 0. So this would be the initial position. And so I have position equals initial position plus initial velocity times time plus 1/2 acceleration times squared. And I'm hoping that that looks very familiar to the equation we saw in chapter 2 about position, right? And so maybe I'm spending too much time here because we got a lot to cover here, but I do want to again keep saying that same thing. Your author tries to get you to see the analogy between everything we did for translational motion. Let's also do rotation, because if you don't see that, you'll become overwhelmed with how much material the author tries to cover in such little bit of time. And the same thing with me here. We're going to try to cover all 9 chapters. Or I really should say 8 chapters this particular chapter, because momentum, angular momentum, your author saves till the next chapter 11 here. But we're going to do chapters 1 through 8, and everything we've done we're going to repeat here. Okay? We're going to try to do that in 4 hours of lecture. And obviously that means we've got to go a little bit quicker than we've been going, but I think and I hope I have, set the stage well then that you're seeing these connections here. And in fact, I'll just take this as an opportunity to say, what else did we do then in chapter 2? Didn't we then say solve this one for time, put it into here, and we got an equation that looked like that? It did not have time in it because we solved the first one for time. We substituted in. We called this kinematic equation number 3. We realized, of course, it was only good for constant accelerations. That was our starting point. But I could say the same thing here. If I were to solve this one for time and put it into here, I would get final speed squared is equal to initial speed squared plus 2 alpha theta minus the initial theta. And so I'd get exactly the same equation. Or we did a fourth one. Or we solved this one for acceleration. We put it into here and we came up with x minus x naught is equal to v plus v naught over 2 multiplied by time. I would have the same thing here in this first section. I could say theta minus initial theta is equal to omega plus initial omega divided by 2 multiplied by time. And so obviously I didn't go through the algebra there, but I think you can if you want to, and I don't even think you necessarily need to, but these would be our 4 kinematic equations. And so our simplest problems would be the ones that, you know, just kind of have something going in a rotation, and it has a constant acceleration, and then we would apply those equations. And the questions may ask, how much time does it take to come to a stop? What is the angular acceleration? What is the angular speed after 3 seconds? How many seconds would it take before it has an angular speed of 80 radians per second? Whatever the questions may ask. But there would be a connection between position, speed, acceleration, and of course time in there. And so those are what we do first. Well, I'll continue on. Because after we did all of this in chapter 2, we then went to chapter really 3 and 4. 3 was about vectors, if you remember, getting us ready for 4. Because that was multi-dimensional. And we have something kind of similar to that. I must say we don't do too much. Because if it's rotating around this axis, couldn't it also rotate around this axis at the same time? That's a little much to do already. So your author doesn't do too much in the terms of multiple axes of rotation. But he does set you up for the future. So for our class, we're going to say, look, it's rotating around one axis. That's good. It's kind of bent. Maybe this side's not bent so much. Okay. But this, I think, is going to be tough enough for us. To have it do this and do this at the same time, let's hold off on those. We will do a couple of things, though. We'll build up to, say, let's say it's rotating and then the axis translates, as I was saying. So by the end of this chapter, we're going to have the problem that I started off earlier was, what if we did something like this? So now we have it rotating and translating. But we will help you set up for your next course. Let's give some direction here. If I take this wheel and I spin it, spin it. What direction is its rotation? Good. You kind of see the dilemma here. You certainly don't want to say left or right because, I mean, if you look at these points on the top of the wheel, from your vantage point, they're going to the right. But these points on the bottom of the wheel are going to the left, and these points here are going down, and these points are going up. So when we say direction, we certainly don't want to say left or right. Those are great descriptions for translational motion. They're not very good for rotation. So I heard somebody say clockwise. Good. And so we will call this clockwise. Although, we might also do this. In your math class, when something rotates clockwise, what do we usually call it? Isn't that a negative rotation? What's a positive rotation? This way? Right? And so that would be a positive rotation. So we're going to use that same convention. We will have positive and negative rotations. And when we say positive and negative, we certainly don't mean left and right. We mean clockwise and counterclockwise. All right? Now, if this will help you remember, it does me. That's a positive rotation. What if this was is it just loose or no, it's actually bent. All right, well, I'll just have to tolerate it here. But this is a positive rotation. Why would we call it positive? Why do we like to call that positive anyways? Well, anybody ever work with a screwdriver and a screw, a wrench and a bolt? If you took a screwdriver and you turned it this way, what would happen to the head of this screw? Wouldn't it come out? Wouldn't it move in the positive Z direction? All right, so that's our convention, and that's how we're going to stick to it. So this rotation is a positive, this sounds a little funny, Z rotation. Let me make it clear. Okay? We use the Z, not that it's actually moving in the Z, like a screw would. If you were to turn it, the head of the screw would actually move in the positive Z direction. This is not actually moving in the positive Z direction, but isn't it rotating around a Z axis? And so the axis is the Z. So we will continue to use that same notation. As you'll see, it is a very useful notation, that this rotation is a Z rotation, even though the particles that are rotating are either moving X or Y or X or Y or some combination. But we label it as a Z-axis, okay? And of course this is a negative rotation. And we'll go back to the screwdriver. If you've ever taken a screwdriver and turned it, if you were to turn the screwdriver this way, what would happen? Yeah, the head of the screw would go inward, which is what direction? Negative Z direction. Okay, and so we will call that a negative Z rotation. So it has direction. And so when we come back over to here, we can put directions with them. We could say that we have theta. We have pluses and minuses of theta. If it goes clockwise, it's a negative. If it goes counterclockwise, it is positive. Same thing here with the speed. Same thing here with the acceleration. I must say the acceleration, though, maybe is sometimes a little bit harder to see. Let's go to translational. Let's say that I was running this way, but I was coming to a stop. All right? I'll say it again. I'm running this way, but coming to a stop. Which way is the direction of my velocity? That way. I'd call positive. Which way is the direction of my acceleration? Negative, right? And so, same thing here. If I come over to here and I take this wheel and I give it a speed and I am stopping it, what direction is its speed? Negative. What direction is its acceleration? Positive, right? Opposite of the direction. That's why it's coming to a stop. If I was starting it up, faster, 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 faster. What direction is its speed? Negative. What direction is its acceleration? Negative. Right? They're in the same direction. And so just like when we did translation, when they are in the same direction, they go faster. And I picked negative there, so maybe I should go back to translation. If I was running faster, 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 which way am I moving? Negative. My speed is negative. What direction is my acceleration? Negative also. They're in the same direction. That's why my speed gets bigger and bigger negative. If I can say that. More negative. Bigger negative. Don't tell your math teacher, but more. The number, the absolute value is bigger. Okay? And so the same thing with direction. Okay? And so really I don't know if there's anything I can really put in this chart to help you to understand that, but I am trying to say here we have directions, and that's what we did in chapter 4. Although chapter 4 we actually did a lot of two-dimensional motion, we won't have 2 dimensions of rotations. And so keep that in mind. We're back to the beginning here. I've erased it, but we're going to be just rotating around one axis. We may be going faster or slower around that one axis. But to rotate around multiple axes, like a satellite in 3-dimensional space, it can rotate this way, which I'll call the y-axis. The satellite can rotate this way, I'll call the x-axis, and the satellite can rotate this way, which is around the z-axis. And so we can have a whole combinations of rotations all going on at the same time. But those multiple axes of rotations is a little much for our first semester. So we don't do too much with that. This will be tough enough, but get you ready for your next class and the next level of class. One last thing on direction. This always helps me. is instead of looking maybe clockwise or counterclockwise, I kind of just take the rotating object, take my right hand, and I look at it, and if I just kind of look at and curl my fingers in the direction that it's rotating, then my thumb tells me what direction it is. So what direction is my thumb pointing? Negative Z. And so we often refer to this as a right hand rule. But don't confuse that with the right hand rule that is coming up next chapter. So we've got many right hand rules. And so I hesitate to say right hand rule, but maybe just for now I'll call it the right hand rule of rotation, because we're going to have other right hand rules, and this is just a convenient one. So we've, as you'll see throughout these next 3 semesters, we got a lot of right hand rules. If I did it the other direction, same type of thing here. I could take my right hand and curl my fingers, and then look which way my thumb is pointing. It's pointing in the positive Z. And that way it could actually become kind of convenient if I was holding it like this. Right? I can then just take my right hand and go, okay, which way is it moving? That way. Okay, so which way is the rotation? Well, I'd call that a negative Y. If it was like this, I might grab my right hand and go positive Y. Okay, and so that makes it an easy way to kind of just find out, okay, what direction is the direction of rotation. All right, well, like I said, we've got lots to cover here, but I think now might be just a good time to kind of pause and connect these two together. I'll kind of illustrate it in the chart by getting kind of rid of the dividing point here. Let's go back to the picture I had up here earlier. The picture I had earlier was some object, point P, some radius R, some angle theta, some arc length S, and as it went around in a circle, and that was just that was the point, it would go around in a circle here, then this object would be moving. And my focus for the last hour here has been on its rotational quantities. But maybe I could come back to this contraption here and say, all right, you see those 3 objects? There's a red one, a yellow one, and a green one. Which one is moving faster? And some of you are saying red, and some of you are saying they're all the same. And I'd say you're all right. It's what are you focusing on here? Let me slow it down a little bit. If you're looking at the distance traveled, which I would call its translational speed, doesn't the red one go faster than the others? But if you're looking at the angle it rotates, don't they all have the same angular speed? And so there's 2 ways of viewing this as it goes around here. And there's got to be a connection between the 2. And so we can look at either the translational speed of these objects, or we can look at the rotational speed of those objects. And so let me come over here and take a look at this. If I look at this here, I can say this object is rotating around. It has an angular speed. And every point on here, no matter where it is, would have the same angular speed. It would go around, say, 1 revolution in 1 second. So it would have a speed of 2 pi radians each second. However, when I talk about the distance it travels, aren't the ones that are further out travel a greater distance? In fact, I would say here that the arc length is related to the angle this way. That's where we started this discussion an hour ago. And in fact, if I took the derivative, I would say ds dt, and I say derivative with respect to time, would then equal r theta. One of the nice things we said about our beginning physics was that we'll treat our object as they are rigid. Now, rigid means what about r? It doesn't change with time. So what can you do with the r? Move it in front. And in fact, you could probably then recognize, what would I call this right here? Isn't that the omega, the angular speed? What's this over here? Isn't that the translational speed? Isn't that how the distance changes with time as this object goes around? And so I would say here that translational speed and angular speed are definitely related. And notice they're related by this factor r. So notice then that the points that are further out here at a greater radius would then have a greater translational speed. So they all have the same angular speed, but they don't have the same translational speed. That's why many of you said, all right, here it is spinning, the red one is going faster. What you really meant by that is the red one has a larger translational speed. Some of you said they had the same speed. Fine. But what you really meant is they had the same angular speed. You guys are probably too old and maybe even were too young to remember probably the days you rode a merry-go-round or the carousel out down on the pier. But as the thing goes around, don't all the horses on the carousel have the same angular speed? But they don't have the same translational speed. Which horses travel the fastest? Yeah, the ones towards the outside edge. And you can see it here in the mathematics. And you can see it when you go down into the pier and watch the people go around. You'll see the moms with the little kids towards the inner part of the carousel, and the bigger kids are out on the outside of the carousel. For those of you into computer and computer technology, you'll see that on the hard drive. The data that is stored out here on the outer tracks is going around or moving at a much greater speed than the data on that part of the track, and hence can be transferred much, much faster on the outer tracks than on the inner tracks. Yeah.
When you're going from x to theta, you got the translational speed on the left side, the dsdt.
Okay, this is more about me saying, let's read the math. Not just do the math, let's read it. I mean, from here to here, I'm just doing the math. I'm just taking a derivative. But what does this mean? ds dt. This is the rate at which s is changing with time. Well, what is s? Come back to this picture. S is that arc length. So you are saying how much has the length grown, right? At what rate is distance changing? Distance changing is the translational speed. And so there's my interpretation from that step to that step. What does it mean? Yeah, it means how does the translational speed change? Another fun one and challenging one here is you get parts of engines like turbos that you get them at 10,000 RPMs, and the points out here are going really, really fast. It's so fast that they need a force holding them together that is usually more force than the material can handle. And they can easily just rip apart. And so one of the unfortunate limitations of a lot of our mechanics is just these high rates of rotational speed and the forces and the accelerations that are required. In fact, you see that next here in the step. I just did speed, but why don't I take it one step further? Why don't I take the derivative with respect to time of that equation? And so I would have dv sub t dt on this side. And then I would have the derivative of r omega here. And as I do the same steps that I did in the last problem, I would say this part is the angular acceleration, because that is how the angular speed changes with time. What would I call this over here? It's back to your question earlier, exactly. Let's read the math. This is saying, how does the translational speed change with time? Well, what would I call that? I'd call that an acceleration. But more particularly, I would call it a translational acceleration. Again, going back to chapter 4, when we had our objects going in a circle here, and let me just take an object here going in a circle. We said this object would have a translational speed. That's the part that made it go faster or slower. What else did we have in chapter 4? We have a a radial acceleration also. That's the part that made it turn. The total acceleration was the two put together. You had a test problem. I can't remember now what it was. Something was going in a circle. Was it a train? Anybody remember the first test?
Car.
Was it a car? Okay. And so the car was going in a circle. And it asked for things like what was the total acceleration. And you had to do both the translational and the radial part. And this much of it is the translational part, right? This is the part that changes its translational speed. And so, again, continuing with my chart, I would say that there is a numerical calculation right here, or a mathematical formula between the translational acceleration and the angular acceleration. And not a surprise, they're connected by this factor r. And so just like their speed were connected by a factor of r, their accelerations are connected by a factor of r.
The translational acceleration is the same as like tangential, right?
Yes, good point. I think we did use that word tangential back in chapter 4. Yes, this is the tangential. This is, and so the t, in fact, I like your author's use of the t, because you can think of it as the tangential that we've been using, or the translational that we're now talking about here. Let me go on to mention the other acceleration we did in chapter 4. We said if you had an object going in a circle, it would need an acceleration to make it turn. Now this is the part of the acceleration that makes it turn, not the part that makes it go faster and slower. So this is the part that makes it go faster and slower. This is an addition to that, the turning part. And if I go ahead and take that v from over here, then this becomes an r squared times an omega squared over an r. And one of the r's cancels off. So the radial acceleration is connected to the angular speed. And again, not a surprise, since the radial acceleration is connected to the translational speed, and translational speed is connected to the, whoops, what's a terrible omega, and I'm missing the square on it. How's that? But not a surprise that the radial part is connected here to the speed, and so this is a, again, nice beginning part here connecting our chapter 4. How are these rotational speeds related to our translational speeds? And so I think you would agree we've done quite a bit here in this first hour together. We have really repeated the converting of units of chapter 1, the kinematics of chapter 2, and then the multi-dimensional kinematics with direction of chapter 4. And so I would say within 1 hour we have done what we did on our first test. And so hopefully that didn't seem that overwhelming, because everything was the same, although we'll probably conclude whether that was too much, too quick as we sit down and do the homework problems and go, oh, how do I do these homework problems? But here's a little trick I like to remind myself. When I sit down to do a problem in rotation, I pause and I ask myself, how would I do this if it was a translational problem? So again, if I have something like that turbofan we talked about earlier, the propeller on an airplane, and it says, how many seconds will it take for the propeller to come to a full stop? It clearly is a rotational question, and I need to recognize that right away. But then if I stop and I think about, what if that question was something a little bit different, like a car that was already moving and said, how long does it take to come to a stop? Those questions I'm more familiar with, and so I kind of change a rotational problem into a translational one and say, how would I do that? And then that helps me say, okay, now what am I going to do for the real problem? And so I ask myself right away, is this a constant acceleration problem? So then I would go to the rotational one and say, okay, is this a constant acceleration, and I should say angular acceleration problem? Because if it is, I can use these kinematic equations. Just like if it was a constant acceleration translational problem, I would ask myself that first. Is it a constant acceleration translational problem? If it is, I would use these equations. And so if it is a rotational one now, and I would ask that, and I would use those. On the other hand, the problem may be more complicated than that. We haven't gotten this far yet, but it may require me to solve it with Newton's laws of motion. Well, as we're about to see, we'll have Newton's laws of motion for rotational stuff, just like we had it for translational stuff. The test you just took, that was one of the things you needed to ask yourself right away. Should I try this problem with Newton's laws of motion, or should I do it with energy? And we're going to see that same thing. If you do it with energy for a translational problem, then do it with energy for a rotational problem. So exactly the same way. The reason I say that is I want to continue on with our learning, but I think that it might be a good idea, instead of going into chapter 5 and 6, because I think those were a little bit harder than 7 and 8, let's do chapter 7. If you remember chapter 7, we had kinetic energy. And we solved problems using conservation of energy. So let's look at those before we look at Newton's laws of motion for rotation. All right, and so I'm going to come over here and say, all right, here is this weird piece of plywood again. Here's where I put a nail right through the center, so I hammer a nail on here. Oh, we've been looking at what we've called point P here. It's a distance r from the rotational point, arc length s, angle theta. Well, we've been saying for a long time it goes around in a circle. But let's ask this question. Does it have any kinetic energy? Does a rotating object have kinetic energy? Well, yeah, I think the answer to that is pretty straightforward. I mean, we just got done talking about the fact that the different points on here have a different translational speed. And their translational speed is related to their kinetic energy. Although I think you can see it's a bit harder here. Don't different points on that object have different translational speeds? I mean, they all have the same angular speed, but they have different translational speeds. In fact, the one at the point right at the center where it's rotating, I would say r equals to 0. So its translational speed really is 0. And as you move further and further out, the points further and further out are going faster and faster, at least in terms of translational speed. So if I were to just say, look at this point P for a moment. Let me just give it a little microscopic size to it. Let me just say that it has a mass of m. I'll call it m sub I. But if I were to look at the kinetic energy of what you might call the ith piece of it, wouldn't it be 1/2 mi vi squared? And if you were to ask, what is the total kinetic energy of this rotating object then? Wouldn't you chop it up into a bunch of pieces, maybe an infinite number of pieces? And as you chop it up, wouldn't you have to add the kinetic energy of each piece until the total kinetic energy? And so wouldn't it be these pieces out here that seem to be going the fastest, that have the most kinetic energy? So this area here does not really have the same energy as that area over there, does it? What would be the total kinetic energy of this rotating object? Well, I guess it would be a summation here. It'd be a 1/2 mi vi squared. Let's see if I can simplify that a little bit. In place of the speed, let me do this. Let me take the translational speed and replace it with the r omega. So this would be the r of the ith piece squared, the omega of the ith piece squared. Now I can make this a little bit easier on myself, because doesn't every term have a 1/2 in it? So I can just pull that out in front of the integral. I would have a half, a half, a half, a half, a half. In fact, let me do one more step here. Mi ri squared. What would you say about the omega of every piece? Isn't the omega the same for every piece? So there's no point in saying the omega of the ith piece. In fact, that's kind of the nice thing of translating the equation from translational speed to rotational speed, is they all have the same rotational speed. In fact, it kind of simplifies that equation even a little bit more, because then I get the kinetic energy total is 1/2, and I'll just bring the omega squared, and then I have a sum of mi ri squared. And this, I guess there's no real way of simplifying that anymore. But let's talk a little bit about it. Let's read into it a little bit. What is it saying here?
Sum of all the masses and bases.
Yeah, it's a combination of mass and distance, right? So it's not just the total mass of the object, is it? The total mass would be what you would get if you just had that much of it, right? So it's a little more complicated than just the total mass. Agreed. In fact, that's the first thing I want you to notice here. That it is really its mass and the position of that mass. And so parts out here compared to parts in here would contribute a lot more to this summation, right? I mean, maybe we should review what these mean. This is the mass of the individual piece, but this is the radius of that individual piece. So things that are way out here are meaning that this number is going to be pretty big. Okay, so it is more complicated, as you guys are pointing out here, than its mass. It's both mass and the position of that mass, what I like to call the distribution of the mass. It's not only the mass, but where is the mass located? So I guess I don't want to call it its mass, but on the other hand, let's pause for a moment. What if this was not a rotational problem? What if this was a translational problem? What if I just had an object and it was moving that way? Had a mass of m moving with a speed v. What would be the kinetic energy of that object? Well, it would be 1/2 times the mass of the object times the square of the speed. Isn't that kind of what we have here? I mean, it's not quite the same. We do have a half, don't we? We have a speed squared, don't we? What's that? So see how it's kind of like mass? It's kind of saying it's resistance to making it go fast. Now, it's not really just mass, though. It's mass and the distribution of the mass. And so our analogy is still going to hold, but I think we have a tougher analogy than anything we saw in the first 4 chapters here. We have something that we'll go ahead and call it rotational mass. And I'll put it in quotes because we don't like to use that word, because if we use the word mass, we're saying, how much mass does it have? And we don't mean that. We mean something more complicated than that. We mean it's mass and then the distribution of the mass. Where is that mass located? And so that's what I'm trying to get to you. You guys in 102 probably use the word a rotational inertia. Does that sound familiar? We're going to use a word that is borrowed from mathematics. We'll call this then its moment of inertia. Probably more accurately, if we want to borrow the word from mathematics, it's called a second moment. You might be familiar with this integral. If you take the integral of x times f of x dx, that is the first moment. So the integral of x squared fx dx is then the second moment. And then so forth and so on. We'll have a third moment, and a fourth, and a fifth, and a sixth. So you can see that that's what we have, don't we? We have the mass, that's its inertia, and we're multiplying it by its position squared. So we have a second moment of its mass, the second moment of its inertia. Probably because we're lazy, we just drop off the second and call it moment. But it's important we leave the word here, inertia. Not just because we need to realize that it is the inertia that we are adding together, but also to realize, I think, the physics of it. What is this thing really saying? This thing is really telling me how much effort does it take to get it to move, to get it to rotate. In other words, what if something had a large moment of inertia? What would you be saying about it? That means for you to get it to rotate, you've got to give it a lot of kinetic energy. That's another way of saying it's hard to get it to rotate. It takes a lot of energy to get it to rotate. Something with very little moment of inertia. What would you be saying? Well, doesn't take much energy to get it to rotate. Or put another way, it's easy to get it to rotate. And so you can see here, I'm camping on this idea for a little bit because I think one of the hardest, there's two hard things in this chapter which fall in the category of the hardest of the semester, is really understanding what is the moment of inertia. And I think you need to understand it both conceptually and mathematically, because calculating these mathematically is hard. Understanding the meaning of all these calculations is harder still. And so I'm starting here with conceptually. What do I mean by the moment of inertia? I'll say it again. It's a measurement. Just like if I was talking about translation, its mass is a measurement of how easy or difficult it is to get it to move. I would say the same thing here. This quantity, which we will call the moment of inertia, is really a measurement of how easy or difficult it is to get the thing to rotate. Notice, it is not just mass. It is mass and where is the mass located. And so if the heavy stuff were in here, this would be easy to rotate. And it probably makes sense why it's so easy to get it to rotate, because as we said earlier, the stuff that's in here isn't going very fast anyways. So you can get it rotating at a very large speed, angular speed, yet its translational speed is not that great, and so these things in here really don't have that much kinetic energy because they're not moving that fast translationally, even though they may have a large angular speed. Fair enough? But on the other hand, if we have some objects out here, some heavy objects, then it's hard to get this thing to begin to rotate. That means this number here is very big. And so this thing called the moment of inertia is just that. It's an indication of how easy or hard is it to get it to rotate. Which, coming and continuing this chart here, means that if I come over here and I'll just continue over here and say, okay, here's my translational stuff, here's my rotational stuff. I'm trying to get you to see that what we've been describing as mass or inertia in translation, then when it comes to rotation, it's a little different. The analogy is still there, but it's a little more complicated. It is the summation of not just how much mass you have, but where is it located. And so sometimes for short we call this inertia, but not to be confused with the real meaning of inertia. It's its moment of inertia. It is both its mass and its position. In fact, what units then would be used for this new quantity. And I'll go back to translation. I think you remember that mass was measured in kilograms. So what units would I have here? Well, mass would be kilograms, and distance would be in meters. And so there is the moment of inertia. And so as you'll see, both for the rest of today and into Wednesday, and even into next chapter, next Monday, which is also next Monday's lab, is next Monday's, not today, next Monday's is I think one of the harder labs of the semester. Its design is to get you to understand the moment of inertia a little bit better. And we take a bunch of different objects and we say things like this. If I take a piece of wood and a piece of metal where they have the same radius, they even weigh the same, they're even colored the same, do they have the same moment of inertia? They don't. Why not?
One is the mass distributed.
It's distributed differently. Exactly. This formula hopefully is saying to you that it's not just how much mass it has, it is also the distribution of that mass. Where is that mass located? So which one would have a larger moment of inertia, and why? This one? Yeah, this one's going to have a larger moment of inertia. Why? Yeah, all the mass is pretty much at its full radius. Fair enough? Whereas this one, as I were to add it up, some mass would be in tight. Some mass would also be out at the full radius. But this one, all of its mass would be out there. And this is one of the experiments you'll do next Monday. You will actually put these on the tray and you run a little experiment. You actually make it rotate, and you have to have a little piece of equipment which measures how easy or difficult it is to get it to rotate. And you'll see this is twice as easy to rotate as this. And so you will again take some time to experiment with this idea. It is this moment of inertia, like I said, which I think is probably the hardest concept, either that or torque, which we will do next, the hardest concepts of this semester. And part of that, I think, is because it is rotation, and I think this rotation by itself is not as familiar with you, and part of it is also, I think that's what you did the least in your 102 class or your high school physics, where you did a lot of translational stuff, but very little rotational stuff. And now we're going to ask you to do a lot of rotation in a very short period of time. But I'm hoping you see the analogy. Anyways, here's the symbol we're going to use. We're going to use the symbol I. That is the one exception I was talking about from the Greek alphabet that we'll go ahead and use here for rotational stuff. And I is a good one, though, because it points out that this is an inertia effect. But what it doesn't point out is that it's more complicated than just inertia. It's inertia and the distribution of the inertia. Although what's really nice about it is that it makes the kinetic energy 1/2 I omega squared. Isn't that kind of nice? Think you can remember that formula for the kinetic energy? Look familiar? In fact, let me put that in our big chart up here. And so our equation for kinetic energy when we were dealing with translational was 1/2 mv squared, and it was measured in units of joules. Now, what am I trying to say now? Well, our equation for kinetic energy is 1/2 I omega squared. What units? It's got to be joules again, right? I mean, all of this came from the idea of energy. It started way back here by calculating the kinetic energy of a single object and then adding it up for all the objects. So it should come out in joules. Let's just verify that. Let's start with this. What units would I use for this new thing called the moment of inertia? Yeah, that's a kilogram meters squared. What units do I use for angular speed? Radians per seconds squared. This is a good example of what did we really mean by radians? Yeah, it's not really a unit. We throw it in there for clarification, or we take it out for clarification. And in this case, I think taking it out for clarification is the way to go. So if I take this out, don't I really have a kilogram times a meter per second squared times another meter, which is a Newton times a meter, which is what we called a joule. So sure enough, not a surprise, after all of this, I will see that kinetic energy is measured in joules, as it should be, as I would expect it to come out to be. But the units look maybe a little bit different, if you will. All right, well, let's do this for a moment. Let's come back to these two examples. Again, you'll be doing something kind of like this in the lab. But let me ask you this. If I were to take these two objects, and I were to hold them up here and drop them, and I would ask, compare your speed when they get down to the bottom. And the reason I'm dropping them is they won't rotate if I just drop them. Fair enough? So this is not a rotational problem. Which one goes faster at the bottom?
The one with the hole in it.
Don't they go the same speed? Well, without air friction. I think you're thinking with some air friction, yeah. Okay. But without air friction, it's kind of a no-brainer question, isn't it? I mean, we did problems like this. I mean, maybe we should run through it again. If I was doing this problem for the first time, I would think of it more as a Chapter 7 problem, a conservation of energy. I would say, all right, you start up at the top, above the ground by some distance y. You let them go. They drop down a distance y. What speed are they going? Okay. And so here it is. Let's give it a mass m, or here's the, well, we'll do the hoop, and we'll do the solid disk. But they both have mass capital M. But if you go to say initial energy is equal to final energy, I would say that the initial energy is mgy initial. And so all those great equations we had from Chapter 7 and 8, there's no springs involved. What else did we have besides springs? There's no initial kinetic energy. And so as it goes down to the ground, it would be a 1/2 mv final squared. Notice that the mass doesn't really matter there. The speed at the bottom then would be that. And wouldn't be the same for each of them? So as most of you pointed out, and we're probably thinking this is a silly question, they go the same speed. Why are you even asking this? Because I want to mix it up a little bit. What if we change it? What if instead we roll it down the hill? And so we start up here, mass M, and we let it roll down the hill. Now, let me give it the same height. In fact, maybe I should have added some clarity to it, because when we go to calculate potential energy, don't we have to pick where y equals to 0? And I probably should have said, in my diagram here, that I am going to pick y equals to 0 right there. Not the ground, but the lowest point the object will go. In fact, maybe this is a good opportunity, since you've just done chapter 9, is to realize that what we did not do when we were in chapters 7 and 8 is we didn't have a size to our object. So what was new in chapter 9 is we had to measure things from the center of mass of our object. So incorporating chapter 9 together with chapter 8, I would like to say here, oops, I said that wrong. This is final position, and I would like to call that 0. And so this up here would be the initial height. And so measuring things from the center of mass, I would be starting at some initial height, and I would be finishing at a height equal to 0. Now, don't get me wrong, the height 0 is not the ground. The height 0 is where the center of mass would be. Or put another way, what I'm calling 0 is the radius above the ground. Okay? And so this object will drop to 0. And I probably should have taken more time to make sure we incorporated what did we just learn in chapter 9 together with chapter 8, because that was a big difference. When we were in chapter 8, when you took the test, our objects did not have size. They have size to them now. And so now I must measure relative to their center of mass. So when I have to pick y equals to 0, remember, I have that freedom of choice of where to pick y equals to 0. And so let's do it cleverly. And in my case, giving it size, I'm going to pick y equals to 0 to be the center of the object. So when I measure how high it is, again, I'm measuring to the center of mass, which, by the way, would also mean that from the ground up to the bottom edge would be y naught, or y sub I. And so that's really what I did in this last problem. And so good, I'm glad I backtracked here, because I think that's a useful one, because that's, again, applying our conservation of energy that we learned in chapters 7 and 8, but it is now applying it to an object that has size, which is what you will be doing if you haven't already done chapter 9. Well, that being said, now I can go back to what I started to do here, is to say, now let's mix it up a bit. Let's have this object roll down the hill. And let me do the same definition, that when it gets down to the bottom here, that is y equals to 0. So I'm going to define y equals to 0 to be the lowest point of the center of mass. It is not the ground level, it is the lowest point of the center of mass. And so let me then define y initial as being the starting height above that. So coming here, I will take the center of mass. I will call this y initial. Maybe drawing a dotted line over here. Then this is y initial. This is saying how high is the center of mass from my reference point. My reference point being y equals to 0, and y equals to 0 actually being 1 radii above the ground level where it's rolling. And so, again, just being a little careful with our chapter 9 and giving it size. But I want you to see this new thing in chapter 10 here is when this thing comes down and I go conservation of energy and I set the energy before equal to the energy after, then when I go mgy initial, what does that equal? What is happening when it gets down here? Is it moving? Yeah, it's translating. So wouldn't there be that? But what else is going on? That is a little different than when we just dropped them and they didn't rotate. What's happening now? We have what we have to add to our conservation of energy. We have another, what you might call, form of energy. This energy is not just going into translating the object, but it's also going into rotating the object. See if conceptually that makes sense. Do you think that the speed down here at the bottom is going to be the same as if I just dropped it straight down? And most of you are shaking your head no. Why not?
Is mass on the side such a radius? On radius are going to accelerate itself.
Okay, but I guess I was looking more for an answer in terms of energy.
Some of the energy will have to go to a rotating.
Right. Can you see that we have the same amount of starting energy? Right? And so you're each problem starts with the same amount of energy. But in this case, all of that energy of gravitational potential energy goes into translational. But what happens over here? Some of it has to go to rotating the object. So what does that say about the translational kinetic energy? It's got to be smaller, right? So we still have our principle of conservation of energy. But what we will see here is that this speed is going to be less than this speed. We've got to give up some of our energy. Instead of giving it all of this to translation, only some of it will go to translation and the other part of it will go to rotational. And so that's the new piece. That's the big step between the last chapter and this chapter, that when we go to add up our energies, we need to include the new form of energy. Let me give you an example. One of my favorite rides is probably so old that you could probably care less about it. But if you've ever gone to Knott's Berry Farm, there's a little ride called Montezuma's Revenge. It's a really fun ride because you start in this roller coaster and the roller coaster is up on a platform. Not a very high platform, but the platform is going to be important here in just a second. But as you stand in line waiting for your turn to get on, people are coming in and out. So here it is. You enter the cart there. As you look down the track, it's not very far, and then there's this giant loop. And you got to sit here and wonder, are we going to get fast enough to go over that loop? How are we going to get enough speed? And then it goes up like this. And one of the best parts of the ride is back there. And so if you're not familiar with the ride, it's simply this. You're on the roller coaster, and all of a sudden you just take off. And you go around the loop, and then go up and come to a stop. Now, why would you come to a stop here? Gravitational potential energy. And then what happens?
Go back down.
Then you go back down, changing the gravitational potential energy to kinetic. You go around the loop backwards. And an important part of this ride is you don't stop. You go through the platform. And you go up again, which to me is always the best part of the ride. That's where your whole insides feel kind of loose and come out. And you're like, oh yeah. Then you go back down. And then you come to a stop going this way. Why? Well, unknown to a lot of people, underneath that platform is a giant, what we call a flywheel. A flywheel is nothing more than a wheel with a lot of mass on it. Why? Because if it spins, it means it has a lot of kinetic energy. And so there's a real simple cabling system. Something looks like this. The cables go around, head off for a certain distance. Then they go around a pulley. Let's see if I can get it right here. They come back, around another pulley, and then around like that. There we go. And so this giant flywheel is just spinning tons and tons of energy. Because this cart, I should have put, well, reaches down and grabs that cable. Reaches down and grabs that cable. Reaches down and grabs that cable. What do you think will happen if that hooks underneath pinch on to that cable? Exactly. And so what's going to happen is this large spinning disc has a lot of kinetic energy. You grab that cable, doesn't that slow it down? Loses kinetic energy, where does it go? To the roller coaster. So this rotational kinetic energy now becomes translational kinetic energy. And enough that it can come through, let go of the cable here. That translational kinetic energy goes around the loop. That translational kinetic energy now becomes potential energy. Goes back down, becomes translational energy. Goes around, still translational energy. Goes up, becomes potential energy. Potential energy comes back and goes kinetic energy, and now we come back here. So what do we do here? Re-grab the cable, because haven't we just slowed down or nearly stopped the discs from spinning? And so if we re-grab the cable, don't we speed this back up? And so we speed this up, giving it the translational energy back to rotation. And so the clever design here is it doesn't consume much energy. It is able to use the energy and store it in a spinning, rotating object until you need it, and then you give it to a translating object. And this whole idea has been around for a long time, and so since about 1950, many people, including locally here in Thousand Oaks, the Kevin Costner company, what if you put one of these in the trunk of your car? A big spinning flywheel. So if you're at a stop sign, where's all the energy? In the spinning flywheel. Then what happens when the light turns green? You, through some clever mechanism, transfer the rotational kinetic energy into translation. And so the big spinning flywheel is not spinning anymore. Your car is translating. What happens when you get to the next red light? You put it back to the flywheel, and so all you do is keep going and stopping, going and stopping. No worries about the energy being lost due to heat. We either put it into the flywheel or we put it into translational motion. I would say it's obviously had some challenge difficulties, and since it's been thought about since the 50s and nobody's built it yet, probably having more success with taking translational energy and converting it back into electrical energy and restoring it. That's what we do with our electric cars these days. We call it regeneration of the braking system. It's a regeneration system, so you recharge the battery. But that's the design. Also run the problem of, do you remember that I mentioned a spinning disc? And so some of these materials, just to get enough energy to move a car, have to be spinning at 25,000 RPMs. And I think the biggest problem they found is they have not really been able to keep the disc together. If you make it out of, say, steel at 25,000 RPM, it just flies apart. The steel is not strong enough to hold it. Last I heard, they've been trying carbon fiber configurations and take the carbon fiber and wrap it up, and I'm not sure how much they've done in recent years with the whole idea of how good batteries are getting and how well we can transfer kinetic energy back to electrical energy, but that's the main idea. Well, I got just 5 minutes here, so I better finish this calculation, but I should also point out there is a very common flywheel. In fact, when I probably used that word name flywheel, I heard many of your eyes look up like, where do you associate flywheels? Automobiles, cars, right? Why does your engine have a large flywheel? And so you've got the engine, you've got the tires, got a transmission, but the engine is trying to turn a flywheel. Why? Because it's a lot of stored energy. And if you know anything about an engine, what will happen is it will burn the gas and push it down. But it has to go around 2 cycles before it burns it again. So you gotta have a big, heavy flywheel for 2 reasons. One, when you first burn that gas, you don't want engine to go really fast. And then 2, you want it to have enough inertia, enough then energy to continue on and finish those 2 cycles so it can go around. And so the big, heavy flywheel has a large moment of inertia, which means it either has a lot of mass or it has a lot of mass at its outer radius so that it can handle the full rotation. And it basically levels things out. It doesn't go really fast when you fire the gasoline, and it doesn't slow down by the time you get all the way around for 2 rotations before you fire the gasoline again. And so flywheels are often used to stabilize things. They keep them from running fast, they keep them from running slow. They're heavy, they're stable, just like a car back here in translation. A big heavy object, it's hard to get it started, but it's also hard to get it to stop. And so it levels things out. Big, heavy objects. Well, I better continue here in this last step here because these are mathematically connected here. And so if I take my next step and say, isn't there a mathematical connection between the angular speed and the rotational speed? Isn't that what we had right here? And so I can put then, in place of omega squared, I can put v squared over r squared. And maybe I should just put final there. And so I can write this as 1/2 m plus 1/2 I over r squared times v squared. And now I can solve this, mgy initial divided by 1/2 m plus 1/2 I over r squared. Take the square root of that, and I would get the final speed. And so notice that my final speed does not look like the equation I had before. This is what I got when it didn't rotate. That's the thing you're going to have to remember as you do these harder problems, that you got to consider not just the translational part of what's going on, but also the rotational part. In fact, to make them look the same, let me take one more step as we run out of time here. Let me factor out a 1/2 m from the bottom. And then, if I simplify that, canceling out the m's and putting the 2 in the top, I think this is a much better form Because now, when you look at this equation, you can see that this equation is close to this equation with some minor effects or major effects depending on how big your eye is. Notice that the numerator up here is exactly the same as over here. So this denominator, which is always greater than 1, right? It's 1 plus a little bit. This is always going to make a speed less than the speed of when I just dropped them. And that was my main point. My main point was being we can still apply conservation of energy. When we did this one, there was no rotational energy. So all the energy went to translational. That's why this number is always bigger than this number. This number then is a little bit less, and how much less depends on eye. Something with a big eye, like this one here, then would have a lower speed than this one. Of course, each of these would have a lower speed than if I just straight dropped them. But this one would actually be going faster down the hill than this one. And on Wednesday, we'll set up a very similar experiment that you're going to do on Monday, and we'll race them down the hill. And we'll see what they come out to be. Question?
Isn't MR squared I?
Oh, careful. No.
Just the sum?
Yeah, this R, yeah, good point. This R is right back here, the total radius of the object. Whereas the I is a summation of the mass and the radius. And a lot of these radii are smaller than the actual radius of the object. So it's not as simple just canceling this. But we'll pick this up on Wednesday. We got a lot more to talk about on this.